Hi everyone, sorry about the wait. My name is Derek Pierre, and I'm head of business development at NuCypher. I know you're wondering why a business guy is doing this talk, but I'm also a software developer, so NuCypher lets me do both. I'm here with my colleague Ryan Caruso, so you can come check us out throughout the weekend. And I just want to talk to you a little bit about NuCypher today. We have a privacy layer for decentralized apps. So for those of you wanting to build privacy-preserving apps, we are the go-to solution for that. At least we think so. And so just a bit about us. A lot of you guys hopefully were at the opening ceremony, so I won't labor on this for too long. But basically, we build cryptographic infrastructure for privacy-preserving apps. And sort of specific to blockchain, we have our data privacy layer, which is our NuCypher network, which helps with secrets management and dynamic access control, so management of sensitive data. And so, I'm sure most of you want to, build a DApp this weekend, but I'm just going to go through sort of where we fit in this space and why apps tend to need us, especially when they're dealing with sensitive data. So how would you share data in a scalable, trusted way, or trustless way, sorry? And so usually, people start off and they say, well, I'll just use public key cryptography. That's great. We all know about asymmetric crypto, private public keys. If you are Alice and you have data encrypted Alice has data encrypted for herself under her own public key. If she then wants to share that data with Bob, she has to decrypt it first and then encrypt the data with Bob's public key. And same goes for Charlie if there's multiple recipients, and that's all well and good. But if you dig into that a little bit more, you'll see some limitations. So the first question is, does it scale? So maybe if you just had to encrypt for Bob and Charlie, that's sufficient. But if you had to do that for 100, 1,000, 10,000 people, that would be very cumbersome. Also, think about if each of these people wanted to access that data at different times. Alice would have to sit down and do this at a variety of times throughout the day. Clearly, it just doesn't scale very well. Oh, and feel free to ask questions as I go through here. So the next problem is the ability to do this decryption. Where does that happen? So the most secure thing is probably for Alice to do this on her client. So Alice would decrypt the data locally and then send the data encrypted for Bob, after she's done that. But, that obviously means that Alice has to be online to do this. So that's not really convenient. And so usually what happens is that you use a service. So that's like your Google Drive, your Dropbox, etc. And you have this service share this data for you. So like share with a link in Google Drive, which I'm sure you guys saw me use earlier. And so now what you're doing is you're really trusting a server with your data, because at some point that data is decrypted. So at some point that data is decrypted on the server. You have malicious actors trying to get in and hack into the server, or maybe even malicious actors working for the service, right? So that's not ideal. And then you're in this sort of decentralized arena or environment, and now you no longer have a centralized service to do this for you. So now maybe you're using IPFS to store your data in a decentralized way, but if you're storing data on an IPFS node, that node is somebody's computer in their basement, and server-side decryption is just not going to cut it. In this case, the malicious actor is the node, or could be the node itself. So them seeing your data in plain text is obviously not ideal. So then you're like, well, shit, like, what the heck do I do now? And that's where sort of NuCypher comes in. So we use something called Proxy Reencryption. And all that is just a more scalable form of public key cryptography so still asymmetric crypto, but it basically allows this untrusted entity, a proxy, to transform or rekey encrypted data from being under a particular public key into being under a different public key. And it does this without that decryption step, nor does the proxy have to know private keys, right? So it just is this ciphertext to ciphertext transformation, and the proxy never sees plain text data. So you might be wondering, well, that's strange. How the heck does it do that? Well, the only way that proxy can re-encrypt the data is by the data owner, Alice, creating this thing called a re-encryption key. That re-encryption key is generated from Alice's private key and the recipient's public key. So you generate one of these per recipient, essentially. And once generated, you can't derive Alice's private key from it. So Alice will generate this re-encryption key, issue it to the proxy, and the proxy says, okay, now that you've given me this re-encryption key, it means that, let's say it's a re-encryption key for Bob, it means that I can now re-encrypt data from being encrypted under Alice's public key into being encrypted under Bob's public key. And again, that's the only thing the proxy can do. The proxy never sees plain text data. And the same can be done for Charlie. So basically, you can encrypt data once under your own key and then delegate access to your data by issuing this re-encryption key. Now, the other part of it is that you might be wondering, well, what about data size, right? Like, what if I have a gig of data that needs to be re-encrypted for some reason? Does that take longer than a kilobyte? And that would be a valid question. So what we've done instead is you can encrypt data with a symmetric key and then encrypt the symmetric key with the public key. So that encrypted symmetric key we call a capsule. So you basically have an encrypted key and then the actual encrypted bulk data. So now, if you think about it, the only thing that needs to be re-encrypted is just the capsule. Yeah?
Can I compare this symmetric key to like a zip file, or it's just a mirror of the original data?
The symmetric key? So the symmetric key is just the symmetric key is symmetric key cryptography. It's the same key used for encryption and decryption, right? So you encrypt data with this symmetric key, and then you encrypt that symmetric key with your public key. And so now the thing that gets transformed by proxy re-encryption is just the capsule. So now the recipient would then re-encrypt the capsule, so now the capsule is encrypted under their public key. They decrypt it to retrieve the symmetric key and then use the symmetric key to decrypt the data. Right? Hopefully that makes sense. So it's a little bit of indirection, but what it enables is that it's now a fixed size because the symmetric key is bytes. So whether your data is a kilobyte or a gigabyte, because you're only re-encrypting the capsule, not the data itself, you're always re-encrypting the same size. And so let's just go through sort of how that would work. So you're the sender has some bulk data. That bulk data is encrypted with a symmetric key. The symmetric key is encrypted. And you store that data in storage somewhere. Like we're storage agnostic. It doesn't matter where you store the data. And then the sender decides, I want to delegate access to this recipient. So the sender will obtain the recipient's public key to then generate that re-encryption key, and then issue that re-encryption key to the proxy. Now, the sender's already granted access. So the sender can go away, doesn't have to be online. That's how we solve the Alice having to be online problem. And now when the receiver wants to actually access that data, they go to storage, get the data that was encrypted. Obviously, that data wasn't encrypted for them, so they don't have access to it. They just see garbage. They then take the capsule, send that to the proxy. The proxy re-encrypts the capsule so that now that capsule is encrypted under the recipient's public key. The recipient then decrypts the capsule, gets the symmetric key, decrypts the data. And no problem. You could do this over and over again for, bulk data, for, chunked, however you decide. And the beautiful thing about proxy re-encryption, unlike public key cryptography, is that you could actually revoke as well. Now, just to clarify, what I mean by revoke is that regardless of what crypto scheme or crypto system you're using, you can't revoke access to data that's already been obtained, right? If I see your address you can't revoke access to your address, right? This is more along the lines of if you think about continuous data. So if you think about things like, let's say you have a heart rate monitor, and you're monitoring your heart rate every minute or every second or whatever. What revoke means is that from the point at which the revoke happens, any further data can no longer be accessed. Any data that you access before that, that's fine, you've already seen it. You can't unsee it. But from that point forward, data is no longer going to be re-encrypted. So the way that revoke works is that the sender just says, hey, proxy, delete the re-encryption key. Now the proxy can't re-encrypt for the receiver anymore, and therefore the receiver can't access your data, any data from now onward.
So is that the big benefit of using the proxy, is this revocation of access?
Yeah, so we sort of look at it as there's three main benefits of using proxy re-encryption. One is that now Alice can go away and have like Alice issues access policies and then can go away. The proxy handles enforcing those access policies. The next part, which I'll talk about in a little bit, is that you can disaggregate the data owner from the data producer. Because of this access, you can sort of issue access policies but still have data be generated in the backgrounds. And the other part is revocation. So those are the three big benefits of proxy re-encryption. I thought I saw a hand somewhere else. Yeah.
So you said you can request a proxy to delete the
Re-encryption key. Yeah.
How do you ensure that they've deleted it? And are you guys thinking about how to ensure that?
Yeah. So you're going to see that in a few slides. But great question. You'll see, I'll talk about the incentives for the proxies. So what we've done is instead of having one proxy, so if you think about it, if you just had one proxy, you have an availability problem, right? Like if that proxy goes down, your data is now not going to be re-encrypted, and therefore you're kind of screwed. So what we've done is we've created a scheme called Umbrel. And Umbrel is a threshold split key re-encryption. So that's a lot of words. All it does is that instead of having one re-encryption key go to one proxy, you take that one re-encryption key and split it into a number of shares, issue each share to a different proxy, and then require a quorum of those proxies to come together to have to re-encrypt the data. So to explain that, let's say, so you could do something like a 3 of 5 threshold, where you say, I'm going to split the re-encryption key into 5 shares. Those 5 shares are going to go to 5 different proxies. And now I'll require any 3 of those 5 proxies to be needed to get the data re-encrypted. And so that's how you create this decentralized kind of network of proxies. Yeah.
Where is that quorum happening?
So that quorum you specify as the policy maker. So you're Alice, you say, I want to issue this access policy for Bob, and I want to force Bob to have to require 3 out of 5 or 2 out of 10. It doesn't matter. It's tunable, so you could tune it to your threat model.
But I guess where are those keys coming together? You said 3 out of 5. Where is that quorum?
So the quorum is what Bob has to do. So instead of talking to one proxy to get the capsule re-encrypted, Bob has to talk to those. Exactly. He has to talk to multiples of them instead. Yeah.
So you said the key is split into 5 pieces?
Yep.
But then they only need 3, Bob only needs 3?
Any 3.
Not 5.
Any 3, not 5. You could say 5 of 5, but again, you still have an availability problem. If one of those proxies goes down, your data is not going to get re-encrypted, right? Because you could only get 4 out of the 5.
You have keys 1, 2, and 5 of the key.
So don't think about it as piece, 1, 2, 3, 4, 5. It's 5 pieces and only 3 are needed. So if you think about it in mathematical terms, if you had 2 variables, like you have a system of equations, you needed to figure out how to solve for 2 variables. But I can create 5 different equations, and you could take any 2 of those equations and solve for 2 variables, if it's a 2-variable equation. So that's sort of the underlying math of it, but that's what we mean by, don't think about it as piece 1, piece 2. Each piece only provides information that you can. Exactly. So the way we do it is with Shamir secret sharing. But instead of like sharing a secret, the secret is the reencryption key. And so this M of n threshold, and so we use this key encapsulation mechanism. That's the capsule that I was talking about earlier. And one of the interesting thing is, remember the proxy is taking in ciphertext, pushing out ciphertext. So if you think about sort of security, with encrypted data, you're not supposed to be able to tell the difference between ciphertext and garbage. So you might be wondering, well, what if a proxy produces garbage? Right? Like if a proxy just returns garbage to Bob, how would Bob know that the data was correctly re-encrypted? So each proxy, when they do a re-encryption, produces this cryptographic proof that proves that they've performed the correct re-encryption. And so Bob can check that to ensure that the proxy has produced correct data. And so what we've done at NuCypher is we have a decentralized, or we're creating a decentralized network of nodes that act, this decentralized network of proxies, essentially, that perform this re-encryption for apps. So it's just like it's like a service, a decentralized service that apps can use to facilitate data sharing. And so it's decentralized, permissionless, and censorship resistant. All we mean by that is this threshold allows proxies to go down, but you can still use it. It's decentralized in that we as a company, we only run a subset of the nodes, but the general public can run nodes on our network and provide this re-encryption service. So if you have some machine, you can provide the re-encryption service if you run our code. And we have like an incentive model for that, which I'll talk about in the next few slides. It's extensible in that, right now we provide proxy re-encryption as a service, but potentially you can add Shamir secret sharing, like just raw Shamir secret sharing as another service on the network that the nodes just run. And one of the cool things is if you decide to use our API, we've written it as characters. So in typical cryptography, you hear about Alice and Bob. We added 2 more characters. And our code is written as in alice.grant to grant access, or bob.retrieve to get the data. And I'll show you that in a little quick demo, time permitting. So we have network characters. There's Alice and Bob. Alice is typically your data owner. Bob's a recipient. We added 2 more characters. One is Enrico. So that's what I mean by proxy re-encryption allows you to separate the data owner from the data producer. And the way to think about, a real good, easy way to think about it is think about it if you have a smartwatch on. And that smartwatch is producing data for you. You could tell that smartwatch, hey, encrypt data with a particular encryption key. And all that smartwatch does is produces data and encrypts it with that particular encryption key. But it's encrypted for me, and I can decide who, I'm Alice, I can decide who has access to that data. So there's that difference. And then Ursula, who's our character name for the proxy. Right, so this is the example of Enrico. Enrico could be like anything. It could be like an IoT device, it could be your car, it doesn't really matter. All you do is you tell Enrico encrypt data with a particular key. Enrico doesn't know anything about data sharing, doesn't know who Bob needs to be. All it knows is that it's encrypting data with this key. And Alice decides who has access to that encrypted data. Ursula does the re-encryption, as we mentioned earlier. And so also, instead of just having like re-encryption keys, you can build policies around this. And what do I mean by policies? That you can make it things like time-based. So I can say, let's say you're working with a contractor, you're only working with them for a month, you only want to grant re-encryption to them for a month. So you could say, here's an expiration on the access policy. Only allow this access policy for a month. And once the month is done, Ursula will get rid of the key, no longer re-encrypt for the contractor. That's the end of it. Later down the road, we're looking into, you can do things like conditional proxy re-encryption. So only re-encrypt if payment was made. So like you could think of, somebody paying you for your data, essentially. And then you could do things like check this smart contract to see if conditions are perfect for re-encryption or some condition has been met. And so you're wondering, how do we trust the Ursula nodes? So we trust the Ursula nodes 2 ways. One is we have a token So all nodes on our network have to stake our token. Our project is a bit different than other projects. We don't use our token for payment. It's purely for staking. So that stake acts as like a security deposit. So if Ursula nodes ever act maliciously or incorrectly re-encrypt data, their deposit gets slashed. And so that's that economic incentive for them to act appropriately. It also, we use a proof of stake mechanism. So, work is allocated probabilistically based on stake. So if you stake, 5% of our nodes, of our tokens, sorry, you probabilistically get 5% of the work in terms of re-encryption work. And this zero knowledge proof that I mentioned earlier, Bob can send that proof to a smart contract, and that smart contract will slash that Ursula if it's verified that they re-encrypted incorrectly. And some of that is based on the key. So if we detect that data is still being re-encrypted for a key that's been revoked, it'll get slashed. And so this is sort of just an overall architecture of what it looks like. Alice can issue a policy to the Ethereum blockchain. She then sends out these policy arrangements to our network here. She could then provide Enrico with an encryption key. Enrico produces data of some sort, or Alice can produce the data herself. It's up to her. Bob then gets the data, has to get it re-encrypted from the network, and then the Ursulas get paid, essentially. And fees for Ursulas are paid in ETH, not in Nu, right? So the Nu work token is only for staking. Some early users, you'll notice a lot of medical data. So if you could think of something like patient control medical records. Let's say you're a patient, you go to see your doctor. You can selectively grant access to your doctor for that visit or for some period of time. If you decide you want to change doctors for some reason, you can revoke access to that doctor and then grant access to your new doctor. There's this concept of data marketplaces like Datum, where you can sell your data to marketers or advertisers. Like, for instance, Facebook makes money off of you right now, but you could decide, I want to sell my browsing history to some advertiser for some reason because I fit their demographic. I could say, OK, if you pay me, I'll then selectively grant you access to my data. Sharing economy, you could think of like a decentralized Airbnb, where if you pay to rent the property, then that data gets selectively re-encrypted for you, because now that you've paid, you deserve to get information on the property. So I just want to show you a quick demo. We're on public testnet on Goerli. So we have a network of nodes. So this is nodes on our network. I don't know if you guys can see that. We have about 91 active nodes right now, all staking Nu. These are a bunch of the nodes here. This is one of them, one, interestingly, that I run. And so what I'm going to do is I'm going to use this network to re-encrypt some data. So what I did beforehand, just to save time on this demo, I have a Goerli Geth node running here. This is Alice. Alice has granted access to a Bob using this command. To save time, I executed the command beforehand. So what Alice is doing here is she's granting access. This is how she learns about the network. This is Bob's signing key. That's how you prove Bob is who he says he is. This is Bob's public key, his encrypting key. This is a label. So what labels are logical groupings of data. So you could say things like a label could be like a folder, or my health data, or my work data, for instance. I set an expiration on it for 2 days from now. This is the threshold. I just use 1 of 1 for demo purposes. This is just to connect to the network. And this is me specifying the payment I'm going to make to Ursulas that control this policy. And so Alice basically issued this policy. And now so this policy has an associated encrypting key here. So now I can say, and when I say our stuff is written as characters, You'll see what I mean here. So this is NuCypher. This is NuCypher commands. I have Enrico commands here. By the way, our code is written in Python. This is just a CLI to the Python. So I can say Enrico encrypt. I can specify a policy encrypting key for him to use, which was the key that Alice just specified. And I can provide a message. It says ETH, Waterloo is fun. Right? So that produced this message kit. So this message kit is that capsule and data that's been encrypted. Right? So that data would typically be stored somewhere on some storage. You know, for demo purposes, it's not. And so now, again, written as characters, you can see what Bob can do. So Bob can do a few things. I can say Bob retrieve. In other words, this is Bob to go get the data re-encrypted and decrypt it himself. So what do I need? I need a label, which I had as ETH Waterloo, I believe. I need the policy encrypting key, which is here. I need Alice's verifying key. That's to prove that Alice is who she says she is. That's here. Whoops. Obviously, I need to provide the message kit that needs to be re-encrypted. Right? Because Bob can actually read that. I need to specify the teacher on the network. And I'll put debug so you can see what's going on. Yep. Exactly. So Enrico encrypted for that policy key that I specified, that Alice created based on the label. And so that data is encrypted under that key. And now what Bob is doing, he's going to take that data, get it re-encrypted, get the capsule re-encrypted by the proxy, and so that now he can decrypt it himself. Exactly, he's going to get the symmetric key, exactly. The capsule is going to get re-encrypted. Symmetric key is going to be obtained, symmetric key to get the data. Right, so what Bob's doing here is just learning about the network. We have sort of a slow learn of the network right now, but that's going to be improved. So Bob number 2 has to have Bob's private key to be able to get it, right? Because remember, the data gets re-encrypted for Bob's public key. So Bob needs a private key to then decrypt the data. Right? So, sorry, this is the data that's been re-encrypted and decrypted by Bob's private key. It's in base 64 because data can be in bytes, right? So if I show you that, base 64 decode, and that's that data, right? So feel free to use our stuff. Check us out. We're on the ETH Waterloo Discord. To be honest, our devs are on our own Discord. I'll show the link in a second. So you can talk to our devs there if you have any questions. We have a bounty here for $2,500 US, and that can be split across teams potentially. It doesn't have to be one person, but just for cool use cases and cool implementations. And here are some cool links to check out. We have like a hackathon repo for you to get caught up on proxy re-encryption and some of these demos. And our docs.nucypher.com has a lot more information on there. Yeah, maybe I'll take a few questions before we stop, just because we started a bit later. Yeah.
Could you just reiterate those 3 highlights you were saying? You can go offline, decouple, and revocation.
Yeah, so disappearing Alice, we like to call it.
So you can, instead of like doing all the key management yourself with your IPFS or your AWS, you can dump the data and then go offline. And
Exactly. You can dump the data, You can even grant access before you dump the data because you know what key you're going to use. So you can issue an access policy, and then Alice can issue an access policy, go away. She can configure Enrico to continue to produce data, and she can go away.
Basically, someone's pinning your access policy for you.
Exactly, exactly.
And then the second one was decoupling.
So that decoupling between the data owner, who's Alice, and the data producer, who's Enrico. That's it. I mean, it's kind of like Alice can go away as well and have Enrico encrypt, but that's what we called Enrico, and then the last one is revocation. We have a really cool article.
Data and the policies?
Sorry?
Replication of the data and the policies, access policies? It's kind of both, right?
When you say replication.
What do you mean by replication?
Revocation.
Oh, revocation.
Yeah.
Not replication.
Oh, no, yeah. Yeah, we have a really cool articles outlining those three things on our blog, if you check it out. Justin wrote it. He likes to call it Disappearing Alice, Enrico, and Revocation. Yeah.
About the scalability you were mentioning before, originally the
Scalability?
public key, you have to do it for everybody.
Yeah, so remember, in this case, Alice is encrypting data once and then granting access to it, right? So instead of having to encrypt data for each individual person that she's sharing with, she only encrypts the data once, issues an access policy to the proxy, and then all the other data owners just end up getting the data re-encrypted without Alice having to do anything. Yeah, she re-encrypts per person, per recipient. But you remember, and again, you're only re-encrypting that capsule, right? But that's not something that Alice has to worry about. That's why Alice can go away. And the capsule is small, exactly.
How about the private key? Where would they store the private key?
Who?
Say Alice and Bob.
Right, so we don't handle, remember, in that process, we don't handle private keys at all, right? Like Alice only issues a re-encryption key, so the proxy never sees her private key. Bob never sends his private key to the proxy either. Bob gets back data that's encrypted for his public key. So the management of the private key is up to you and your app. Yeah.
It has to be kept secret by Alice.
Well, yeah, I mean, yeah, that's what you want for a private key, right? Like only Alice and Bob should always have control over their own private key and never expose it to any external entity. Yeah.
We're a few minutes over.
Yeah, we started a bit late, but yeah. Maybe one more question? Yeah. Yeah.
Let's say Alice encrypts the whole album of 11 songs.
Yeah.
And then she just wants Bob to have access to songs 5.
Right.
Can't she do that in the label or once she encrypts and updates
Yeah.
for the album then?
Yeah, so that's where Alice has to think about the labels, right? Because you're granting access per label essentially. So what she could do is, if she wants a per song granularity, each song should be its own label. And then she creates policies per song, exactly. Yeah, exactly. So you can just think about it as like a folder, right? Like if you do the label as the folder, then everything in the folder is accessible. If you do it per file, then only each file, right? So Ryan and I are around. Feel free to come to our table and ask us more questions if you like. And thanks, guys.